Okay, so we're going to look at our first exam question in the elastic collisions in 2 dimensions topic. So in this case we're going to be looking at oblique collisions. So remember, with oblique collisions, the angles at which the objects hit each other is relevant, and the angles at which they depart after their collision is relevant. You've got conservation of momentum in the horizontal direction. You've got coefficient of restitution being a useful property that you can make use of in the horizontal direction. And in the vertical direction, you know that the components of the velocities remain the same. And when I use the word horizontal, what I really mean is along the line of centres, the line connecting the 2 centres of the spheres, which we usually take in our diagram as being a horizontal line. And when I say vertical, what I really mean is the vertical, the direction which is perpendicular to that line of centres. Okay, so you can review the topic if you need to, or you can just jump straight into the question. But either way, do have a go of it yourselves first. Pause the video now. Okay, so the first thought probably is that you're not really given that much information in this question. We sort of have to work through things quite a bit algebraically. One thing though that we want to get first is to understand this angle that the object's moving at. Let me just draw this slightly bigger. So you've got these 2 circles, and you're told that, okay, from the centre and then up to a tangent point here, let's say, that's at least the direction of motion, and we know that they're the same size, so this yellow line that I've just drawn there and this other little yellow line I've just drawn there, those are both the same length, because we've of course got, you know, the centres of the spheres here. You've also got that this yellow line that connects the centre of the right sphere to the tangent point, that's also going to be 1 radius length. Let's give it a name. So this is, say, A, and A. And therefore this angle theta we can now determine, right? And the reason we can do that is because we know that this is a right angle here, because we know as a property of circles that a tangent to a circle is going to be perpendicular to the radius which meets at the same point. Okay, so that then tells us that we've got tan of that angle. Oh, let's not do tan, sorry, it's hypotenuse and opposite, isn't it? So that sine of the angle is equal to the opposite over the hypotenuse, so that's a over 2a, that's a half. Okay, and therefore theta is going to be equal to 30 degrees. So just to be clear, that 30 number that we've just come up with, that's technically completely unrelated to the 30 degrees given in the question. That 30 degrees is the angle at which this left particle, I guess it's called Q, that's the angle at which it's moving relative to the line of centres, the horizontal line of centres. It then will bounce, this left ball, it will bounce here and then continue on at an angle 30 degrees even more so than that, which is what we're told in the question. It turns an angle of 30 degrees. So from 30 degrees it turns 30, and therefore it ends up doing 60 degrees. So let's just quickly draw that situation as a before and after diagram. Okay, so I've drawn sort of a pairs of spheres. We're going to call the first one the before, and this one here the after. And in the first case, we know it's going, you know, in this sort of direction. Let's say that's then 30 degrees. And in the after case, we know it's going at about 60 degrees at whatever speed. The speed we don't necessarily know yet, but we know it's going at 60 degrees. Okay. Let's call then the initial speed, let's just call it u, Okay, and with these kinds of questions, you always have to be careful about the distinction between vectors and scalars. Sometimes it makes sense to use vectors, sometimes scalars, sometimes a bit of both, as long as you're clear which one you're using. So here, this u, I'm using it as a scalar. So that's the magnitude of that vector there. And having labelled that one u, we can therefore, we'll come back to that after actually. And then for this sphere, Q, in fact, let me just quickly label these to make it clear. So that's P and Q, and that's P and Q. The before case for Q is that it's going at a speed 0, isn't it? And then the after case for Q, when it's hit, because it was stationary, that must mean when it's hit, over here, it's going to move off in the direction of the line of centers. Okay, that's just a sort of, it's intuitive, hopefully, to you. If something that's not moving is hit by something, it moves in the direction that it was hit by, and the direction of the impulse, effectively, and that is the line of centers. So Q's direction of motion in the after case is just going to be to the right-hand side. So we can draw that as a speed, I suppose, here, going to the right, some amount, don't know what it is. Let's call it, say, W, and I've skipped out V because that's what I'm going to use here. I'm going to call that one there V. Okay, so these are all scalar quantities, and we've got the directions for P in both the before and after, and technically we've got the directions for Q as well, because for Q there is no direction, it doesn't move, and for after the direction is effectively an angle of 0. It's moving to the right. Okay, now we need to form the relevant equations. So let's do conservation of momentum first, COM, in the horizontal direction. And let's then see, so before we've got the object P moving at a speed horizontally of u cos 30. And its mass, let's just say it's m. And that's going to be the same as the mass of Q. And then the speed of Q is 0, so therefore that's all of the momentum that we've got in the before case. And that's going to be equal to then V cos of 60, I should really say times m again, plus, and then in this case, the W speed, that's entirely horizontal, so that's mw. And if we then cancel out those m's, we get u cos 30 equals v cos 60 plus w, and that's going to be the same as root 3 over 2u equals a half v plus w. And that, we'll leave it as it is for now, in fact. And then let's look at the other possible equation we could use here. So that's going to be the coefficient of restitution. So draw a line of that. Let's do coefficient of restitution. So we know that E is equal to, so now remember we're talking horizontally, separation over approach. So the separation is going to just be the horizontal W minus the horizontal component of this speed V, which is just V cos 60. So that's W minus V cos 60 all over, and then approach is going to be the horizontal here, horizontal speed of P, which is U cos 30, and then technically a minus 0. And then if we simplify that, we get W minus a half V, yeah, that makes sense, half V all over root 3 over 2 times U. Okay, and we've got our two sort of key equations there. We've got this one from conservation of momentum, and we've got this one from coefficient of restitution, and that is to say we are still trying to find this value. We're still trying to find this value E. So we'll do that in a moment now. And the way we're going to do that is by just manipulating these equations appropriately. So let's bring our first over here and our second across. And as usual, you can always pause and have a go at manipulating yourself if you didn't reach this point by yourself. But if not, then let's think about what we want to substitute to get rid of and what we can sort of keep. And as you can probably see, it's two equations, right? But each of them has three unknowns, so presumably we're still missing a little bit of information here if we're going to try and find a specific value for E. What I haven't done yet actually is the vertical consideration. So remember, in the before case it was 30 degrees and we called this U, and in the after case it was 60 degrees and I called this V. And we know in both these instances, because the vertical component of the speed shouldn't be effective, we know that these are equal, shouldn't be affected even. So we have here, the vertical going upwards, that's U sine 30, and here we have V sine 60. So in other words, we have root 3 over 2 U, oh sorry, wrong way around, hang on, that'll be a half U. So half U and then root 3 over 2 V, those are going to be equal. So let's make a note of that as well over here. A half U equals root 3 over 2 V. And that's our third little bit of information. And with all those three, that should be enough then to get us to the point where we can then figure out E. So let's see how we can do this. 3 is the same thing as the root 3 over 2U equals 3 over 2V by multiplying by root 3. So then combining 1 and 3 together, we've got 3 over 2V equals a half V plus W, and that implies that V equals a half W. No, sorry, 2 over 2 cancels to 1, doesn't it? So V equals W. Yeah, it'll just be V equals W. Okay, that comes out nicely. And then let's see what else we can combine. So over here we've got another root 3 over 2U. So we could probably sub that one in quite nicely. So let's do that actually. So 1 and 2, that gives me E equals this. And then we know that V is equal to W. So let's just pick one. Let's turn W's into V's, say. Okay, and we get on the top half V, and on the bottom 3 over 2V. And that, of course, all cancels out nicely. We get 1 over 3. And there's your answer. Coefficient of restitution is 1/3.